All right, hi everybody. I'm just bringing up my document camera here. Okay, this is notes for lesson 0.7, and we are looking at rational expressions today. You have a simplified rational expressions worksheet that you'll need to complete and turn into Student View when you're done, hopefully before Sunday, as soon as possible, really. And so this is simplifying rational expressions. So first of all, what are rational expressions? They are rational fractional expressions. So we are simply doing 3/4 times or plus 2/5 today. Okay, it's not quite that simple, but the first thing we want to remember is that we want a common denominator. And sometimes it's easier than others. So for instance, these two denominators don't have any common factors. And because of that, the easy thing to do is simply multiply by 5 on top and bottom for the first fraction, and by 4 on top and bottom for the second fraction. And again, the logic is that we're multiplying by 5 over 5, or 1. So by multiplying by effectively 1, we're not changing the value of what we started with. This becomes, 15/20 plus 8/20, which would be 23/20. And this is a perfect improper fraction. It's totally fine. However, sometimes we have fractions that are, I don't want to use 2. Let's do 5/6. Sometimes we have fractions that actually have common factors where I don't actually want to multiply by 6 top and bottom here and by 4 top and bottom here. It works, but it could make it harder. So what we want to do is figure out, let's first say, hey, I know that 4 is 2 times 2, and I know that 6 is 2 times 3. So they already have this factor in common. And so to make life easier, I want to multiply by the smallest thing to make them have a common denominator. So I'm going to multiply by a 3 so that it gets that 3 factor in the denominator. And then I need this extra 2 over here. So I'm going to multiply by 2 top and bottom so that we have a blue 2, we have the purple 2, and the red 3 for everything. So those are factors and 2 things that multiply together to give you what you want. And so it turns out that 4 times 3, the denominator happens to be 12. So that becomes 9/12 plus 10/12, or 19/12. And that is the best way to do it because I can't reduce now. If I had just multiplied by 6 and 4, then I'd have to go and try and factor some more to reduce this. So if we're very careful, we want to look at the individual factors. And that's what we really want to remember when we're looking at rational expressions. But before we get to the nitty-gritty, example 1, find the domain of the expression. What values of x don't work? That's domain. I talk about domain a lot of different ways. The first thing I want to talk about is what domain looks like. So domain is really the picture that you see when you graph something. And we can pay attention. You guys will get really good at this year. When we look at this, hopefully you know that 2x squared is a parabola. And so when we go to look at it, you know that it's a parabola. And we also have an understanding that this parabola has little arrows on it, and it continues on, getting wider and wider and wider and wider and wider forever. And so it's not just on a 10 by 10 grid and this is it. It really goes on forever. And so you have this idea that this parabola keeps extending. When we talk about domain, it's really domain. How far does the graph go from left to right? And so when you think about that parabola extending out forever to the left and forever to the right, then that means that it has all the possible x values. So this is a parabola. It goes forever left and forever right, meaning it's just extending up forever to the left and to the right, from negative infinity to positive infinity. And what that means is the domain is all real numbers. I use a capital D for domain. We can write all real numbers if we want. But we have another thing that we can do that's maybe a little bit easier. A couple other things that work. You can use the boldface R, which is you draw 2 bars, 2 vertical bars, and then overwrite that R shape. That means the same thing. So this is the formal math notation for the real number system. And so you can just write the boldface R. You can also say it goes from negative infinity to positive infinity using parentheses. And this is interval notation is what this is called. And I like interval notation. It means the same thing if we were to say that we want x values that go from negative infinity to positive infinity. X values greater than negative infinity and less than positive infinity. This is inequality notation. And it has inequality symbols. With infinity, you have to use less than, because you're never going to get something equal to infinity. That's the definition of infinity. It's just one more. Oh, just one more. One more away. Oh, not quite there yet. Yeah. So you can never actually equal infinity. So we always have to just use less than or greater than in this case. And same thing, that's what the parentheses mean. It means you cannot actually ever achieve negative infinity or positive infinity. Get close, but no cigar. So there's all these different ways. There's 4 different ways that you could answer this. So this is just a parabola. All polynomials have domains of all real numbers. So any polynomial has a domain of all real numbers. Polynomials are nice smooth curves that just go on forever. The problem comes in when we have fractions. Fractions are problematic, and fractions are problematic because denominators cannot equal 0. So anytime you see a rational expression, which is what this is, rational fractional, in order to figure out the domain, all we have to do is look at the denominator. X squared minus 7x plus 6 is not allowed to be 0. So we need to figure out what x values actually equal 0, and then we can exclude them. Okay, everything else will work, but these guys. To figure that out, we're going to go ahead and factor. Double bubble, so x times x is x squared. What times what gives me positive 6, negative 6, and negative 1. We're going to go ahead and solve x minus 6 cannot equal 0, x minus 1 cannot equal 0. And by moving the 6 over and moving the 1 over, we get x cannot equal 6 and x cannot equal 1. And that's the domain, and that's the easiest way to write it. X cannot equal 6 and x cannot equal 1. You might be able to write x cannot equal 1 or 1 comma 6. That also probably works just fine. I think I understand that as well. So either one of those works for writing the domain. You can do it using interval notation, but we'll talk more about that later. And radicals. And even radicals, actually, are the other things. So right now, you're going to learn a lot more about domain, but these are the 2 things that you need to remember now. Rational expressions, denominators cannot equal 0. So anytime you see a denominator, you need to remember, hey, you can't be 0. That is, I expect you to know that. The other thing is, if we have an even radical, if it's an odd index, like a cube root or a 5th root, it's all real numbers. It goes on forever. So I'll go and I'll show you the graphs of these so you can see how these domain pictures, these domain values affect the graph. I'll show you. Square roots. So this is a square root because it's got the little invisible 2 there. A 4th root, a 6th root, an 8th root. Even radicals must be greater than or equal to 0. Always, always, always. They must be greater than or equal to 0. They must be positive or 0 because I cannot take the square root of a negative number. I can't. It's imaginary. It's not there. It doesn't really exist. okay? So anytime you have a radical, even radical, all we need to do is say, hey, you must be greater than or equal to 0. And then we can go ahead and solve that. Well, get rid of your radical. We're just going to square both sides. The square and the square root cancel out, leaving 3x minus 7 is greater than or equal to 0. And then I can just solve for x. I'm going to go ahead and add 7. So I get 3x is greater than or equal to 7 and divide by 3. So we get x is greater than or equal to 7/3. And remember, if you happen to have that was a negative, let's say it was negative, right here, 3x is greater than or equal to 7. And we had to divide by a negative value, then you must flip the inequality. So x would become less than or equal to negative 7/3. Okay. Be very, very careful. Don't forget that little property. When you multiply or divide by a negative value, you flip your inequality symbol. All right. So this is the domain. The nice thing here, when you're solving this little equation, this is the domain for this radical. Let me show you what that looks like. I'll just show you on the Texas Instrument since I have it right here. If you wanted to put this in your calculator, you would absolutely have to include parentheses. So be very, very careful. I'm going to put parentheses around x squared minus 1, parentheses around the numerator, and you can't see that, there you go, parentheses around the denominator, x squared minus 7x plus 6. And so I've got that typed in. I'm going to do a zoom standard window. Funny. I give you an interesting graph here. This is unintentional. So here's something interesting. So first of all, you'll notice that this graph is not a nice smooth curve like our lovely parabola. In fact, this graph looks like little sort of inverted L-shaped things, and that's typical of rational functions. And you have this point here where the graphs diverge. They go in different directions, like probably you and your parents sometimes. Okay. So what happens here is what's called a vertical asymptote. And the nice thing is you can actually test this. So 6 is where it's happening. If you hit trace and then type in 6, so I'm literally pressing 6 and enter, you'll notice that it gives you an output of nothing. Why is nothing? Really, it's undefined, and that's what's happening because the 0 is under, it's undefined. There's nothing there, and it creates, every time you have something undefined, it creates this undefined space. Sometimes it looks like this is, it's called an asymptote, but other times, watch this, we're going to do that again. I'm going to trace 1, enter. And there's another thing here that's undefined at 1. That's actually a hole in the graph. I'm going to zoom in around x equals, oops, didn't work. Zoom in. I'm going to just move my cursor to 1. So I'm a little closer. You can't really see it, but if I do trace 1 here, it's undefined. There's a hole in the graph. I don't know how close I have to zoom in, but there's a gap, a little hole in the graph, which we'll talk more about a little bit later. I also want to show you the second graph. I can do this square root function in my calculator. Second square root, 3x minus 7. And I'm going to go ahead and do a zoom standard, another standard window. And you can see this is a square root function, square root swoop. And it's been shifted over to the right a little bit. Well, it turns out that it's actually equal to 7/3. So I can do trace 7/3, and its value is actually 0 right there. That is called a terminal point. It stops and starts right there. So it starts and continues on for that square root swoop. And you can see, so the x values that are shown on this graph are every x value greater than that 7/3. So it starts at 7/3. 3 is included, 4 is included, 5, everything bigger than 7/3 we have a picture for, okay? Pretty interesting. All right, so those are 2 things about domain you must know. So example 2, write the rational expression in simplest form. So it must be reduced. State the excluded values. Oh, okay, I can't state the excluded, yes I can actually. This one's very interesting, that's kind of weird. The excluded values means what's not included in the domain. So for that, so I'm gonna always, I just do that first. X plus what, oh sorry. I love that my pen's erased. XY plus X cannot equal 0. This is a very interesting one. You'll notice that there are 2 terms here. There's a GCF. They have an X. I'm going to take out the X. When I take out the X, I leave Y plus 1 behind. And so we're going to set each piece not equal to 0. So it tells me X is not allowed to be 0, and also Y is not allowed to be -1. So those are the excluded values that are part of the domain, or rather excluded from the domain, okay? So X is not allowed to be 0, Y is not allowed to be -1. Okay, so then we want to simplify these. And to do that, I'll use purple. Here we go. I always want to factor if I can. You must factor first. And in the top here, it's a monomial single term. I can't really factor it. They're already factored, 3 times x times y. And our denominator, we just factored it. It has a GCF, so we're going to take out that GCF, leaves behind y plus 1. And now that it's fully factored, and what that means is everything's written in terms of multiplication. And when things are written as a product, so all these things are being multiplied, and here we have 2 things that are being multiplied. When things are multiplied, then you can reduce them. So we can reduce because there's an x on top and an x on bottom. X divided by x is 1. It reduces and leaves behind 3y over y plus 1. And we always just want to remember that we got rid of the x. It's really important that we keep that along for the ride. If we didn't have that there, these 2 things are not technically the same. All right, we want to be sure that we make sure that we don't, 0 is not possible, because I could have x is 0 here. There is no x. It could be anything. I also like keeping the other one along for the ride. This is called a implicit domain, and this is explicit. Right here is an implied domain. Y is not allowed to equal 1. I like to state it. I just like to be explicit about things, just tell you what it is. So this is fully simplified expression, and this is the restriction on the domain for those variables. Kind of a weird one. Again, over here, we're going to look at what are the excluded values, and that just comes from the denominator. 4 minus x squared cannot equal 0. The denominator cannot equal 0. There's a lot of ways to solve this. I'm going to go ahead and factor it, I guess. So 2 minus x and 2 plus x, it's difference of squares, which means that x cannot equal positive 2 and x cannot equal negative 2. And again, that's part of the domain, excluded from the domain. Every other x value will be just fine. Let's go ahead and factor. So up here, I noticed that there is a greatest common factor of x. So we're going to go take out that x. That's going to leave me with x squared minus 5x plus 6 over my denominator. You know what? Actually, I am actually going to go ahead and do this. I'm going to rearrange these terms because the order, is backwards. So I'm going to rearrange it as negative x squared plus 4. I'll talk about why in just a second. And then I noticed that there's this negative 1 out in front. So I'm going to go ahead and take out that GCF as well. So then it leaves x squared minus 4 behind. But there's this negative 1 out in front. Then I still can factor this trinomial up here. So I'm going to double bubble. X times x is x squared. And then what times what is positive 6? Be very careful. Positive 6 is 2 times 3, or negative 2 times negative 3, or 6 times 1, or negative 6 times negative 1. We want a positive 6. The signs must match. So in order to get the negative 5, we would go with a negative 2 and a negative 3. And then this denominator is difference of squares, so it becomes x plus 2 and x minus 2. And now you'll see that we have some common factors. So what we're doing is factoring everything. So x minus 2 on top and bottom divided by x minus 2 is 1. It goes into itself one time. It reduces. And so this is a great final answer. X times x minus 3 over negative 1 times x plus 2. That's a great final answer. Now, so maybe you're wondering why I rearranged it instead of just factoring like I did here. I could have. So I'll do that in green. Imagine if I had just factored the numerator, just like we did, but I just did the denominator going directly from here. So 2 plus x and 2 minus x. So you are totally allowed to do that. But you have to be a little bit careful. The x minus 2 and the 2 minus x do cancel. They're very, very similar factors, but they're not exactly the same. These are actually called opposite factors. And it's a good idea to, be on the lookout for them. But you'll notice they're exactly opposite. This is a positive x and this is a negative x. Here we have a negative 2 and this is a positive 2. So within the factor, those terms are opposite, exactly opposite. And so what happens is when they reduce, they don't go in one time. They're opposite. So there's actually a negative 1 that gets left behind instead of a positive 1 left behind. And that's where that negative comes from and why it's there. Okay, it's because they were opposite factors. They weren't identical factors. So be very, very careful. It's a good thing to look out for. And we should also include our domain here. X cannot equal 2 or negative 2. All right. Always a good idea to be thinking about domain. Denominator, domain, denominator, domain. All right, so you're going to have some multiplying and dividing rational expressions. Multiplying, very, very easy. Factor first is the rule. I don't need to think about a domain on these. They're not going to ask what's the domain. So we're just simplifying, just working on the skill. I want to go ahead and we're going to factor this first trinomial. Is there a GCF? No, there is not. So I am going to double bubble. 2x times x is 2x squared. What times what is negative 6? Let's see. I think that's going to be a positive 2 and a negative 3. And how do you know if you did it right? You check the smile. Okay, so 2x times 2 is 4x. And negative 3 times x is negative 3x, and 4x minus 3x gives me positive x. So I know I did that correctly. Don't feel like you have to erase the rainbows or smiles, whatever you want to call them. That's work. That proves to me that you're doing something, and I know what that means. Let's look at this trinomial here. That's an easy one to factor. X times x is x squared. What times what is negative 5? That would be a positive 5 and a negative 1. Times is really, really nice because when you multiply a fraction, you just go straight across really simply. And so up here, ooh, this one has a GCF. So we want to take that out first. I'm just going to smush it right here. Smush it. Da, 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 da. Okay. It had a GCF of x, so I just took that x out, leaves behind x squared minus 3x plus 2. And from here, I'm going to go ahead and double bubble. x times x is x squared. What gives me a positive 2? A negative 2 times a negative 1 would give me a positive 2. But when I check my smile, it will give me a negative 3x when I add them up. All right, and then down here, oh, again, they gave me a GCF. This says a GCF of 2x. So I'm going to go ahead and pull that out. That would leave behind a 2x and then a minus 3. Oh, and that's all I can do. 2x minus 3. Okay, I didn't need to do that in 2 parts. Okay, good. So the nice thing is I don't need to do a step where I just put them all together, though technically that would be the mathematically correct thing to do, but it's really annoying. Once everything is factored, once you've factored as much as you can, then you can start crossing things off. So let's see, I have, oh, that's a purple, I made black. Okay, 2x minus 3 goes into 2x minus 3 one time. I have x minus 1 goes into x minus 1 one time. I have an x that goes into x one time. And that's it. So what's left over? My purple x plus 2 is left over. My blue x minus 2 is left over. All times 1. And then in the denominator, I have a green 2 and a red x plus 5. And this is great. You do not have to multiply these things out together. Don't bother. Just leave it factored. Factored is the winner. When things are factored, we can tell a whole lot about what's happening graphically. So we'll talk more about that later. Here, x cubed minus 8, that is difference of cubes. Yay. So that's going to factor small bubble, big bubble, minus plus plus, x being cubed minus, what's being cubed? 2. So this is minus 2 being cubed. Whoops, cubed. Okay. So my base is x and a 2. And I'm going to square the first thing. X times x is x squared. Multiply in the middle, 2x, and square the last. 2 times 2 is 4. And here, my denominator is going to factor x plus 2, x minus 2. This is the big change. We don't divide by fractions. What do we do instead? We always, always, always multiply by the reciprocal. Dividing fractions is a no-go. It just doesn't work. It's so confusing. And so instead, we're just going to flip and multiply. So you're going to change your sign, and we're going to flip these around. So instead of x cubed plus 8 being in the denominator, it's going to flip and move to the numerator. That, again, is sum of cubes. So small bubble, big bubble, plus minus plus, and it's x and a 2 that are being cubed, same as above. Square the first thing, multiply in the middle, square the last thing. And then this portion, I used purple, x squared plus 2x minus 4 is going to move to the denominator. That does not factor. Does not factor, and so that's all we can do there. And let's see what cancels. X squared plus 2x plus 4 goes into itself one time, and x plus 2 goes into x plus 2 one time. X minus 2 goes into x minus 2 one time. So multiply by the reciprocal for every division problem, and life will go very nicely. Are things always going to cancel out? In the wonderful world of math, most things will. In real life, probably never. Who knows? But these are all skills that we're using to help us manipulate large things into things that are much neater and more compact. You can see we started pretty crazy, and this is much better, isn't it? And that's the goal here, because to be able to manipulate something and really compact it down is going to help a lot later on. All right, ladies and gentlemen, hopefully that worksheet won't give you any grief. But again, if you have questions, please write them down, try and fix your mistakes, check your answers. And if you have any questions, come see me during office hours later. Have a great day.